Hi.
Hello.
Hi.
Wait, so only 3 people? What happened? No. Okay, so everyone is here. All right. So I think last time we did. Last time I think we did that. If mu is the super compactness measure on E omega 1 R, then pi mu omega 1 is equal to theta. Oh, Lucas, are you joining again? Hello? Lucas, are you here? Yeah. I don't know what happened. There are 2 of you. Okay. So this is what we did last time. The other basic thing we need from the theory is assume ADR. Every set of reals is R R UB. Okay, so what does this mean? Definition. So suppose A is a set of reals and X is a set. Then we say A is X UB if there are trees. So there are complementing trees. There are trees T and S, such that for any poset of size X, if T is a poset of size X, so I mean we are in the choiceless context, so this means there exists surjection on P, right? So if P is a poset of size X and G is generic, and then yeah, one projection of T is A, and 2 VG thinks projection of T is the complement of projection S. Right, so T and S are trees on ordinals, omega cross kappa. Okay. So the poset can be of size X, meaning X projects on P, right? Okay, so what you want, if you, I mean, so we need to prove, because I'm proving most of the basic facts when I'm doing it. Let's just do this. It's not too hard. So proof of the well, it is quite hard if you start from the beginning, but if you assume some things, then it's not so hard. So the main thing you need to assume is so ADR implies that every set of reals is Ruslan. i.e., if A is a set of reals, then there is kappa less than theta and T on, so 3 on omega n cross kappa n less than omega, such that equals projection of T. This is what it means to be Suslin. And ADR implies every set is set of reals is Suslin. Now, how exactly you prove this by no easy proof comes to mind. I don't know if there's an easy proof. But if you do the analysis, scale analysis, then this will come up there. ADR implies there is no largest. Oh, maybe that's easy actually. Maybe that's how you could prove. Yeah, well, I don't know. I'm not sure if there is an easy proof. But if you check Paul Larson's book, I'm sure there will be a proof of this. If not, then it's in the Cabal somewhere.
There is a proof of this in Paul Larson's book.
Okay. Yeah. Yeah. Okay. So, well, okay. If you use this, then, well, so it's easy to see that for countable posets, right? So here's an easy level for ADR implies every set is omega Suslin, meaning, you know, X Suslin meant that X subjects onto it, omega Suslin would mean omega subjects onto it. Because if you just take T and S, and then your forcing is countable, right? So, so how could you prove this in an easy way? You could say, let me try to write the proof and see if we can simplify it. Okay, so proof would say, suppose not, right? Or fix, well, it's the coin forcing, right? And so fix A.
Sorry, did you mean to write something else? You wrote every set is omega Suslin?
Yeah, because I defined X Suslin to be where X subjects onto P.
But you mean UB, right? Not Suslin.
Oh, UB, yeah, UB. So for countable posets, which is just a coin, adding a coin real, basically, right? So fix a subset of reals and let TS be trees for A and A complement. Okay, so we can work, it's enough to show, right? Enough to show that if G is as 1 omega generic over L A T S R, then L A T S R G thinks that projection of T is R. I mean, it's not the same R, right? So RG minus projection of S. But this is easy to prove because I can take a countable substructure, right? So this is easy to prove. Okay, so to see this, right? Fix some alpha sort of bigger than eta, for example. And we want to see that L alpha A P S G things projection of T is R of G minus projection of S. Now, if you remember from last time, what I can do is I can find sigma. Now remember, because you can find sigma in T omega 1 of R such that L alpha A intersection sigma E as sigma intersection reals is just sigma. Okay. So I guess what you want to do is that you want to pick the name. So suppose it's not like that, right? Which means there is a real which is in neither of them, and there is a condition which forces that. Let's see. Oh, I see. I don't really need TNS. So TNS will be okay. What I need to do is let me backtrack a little bit. So what I need is okay. So TNS are on some kappa. Remember, the TNS were on a kappa which is less than theta. So there is a set of reals that codes it, right? So let P be such that this alpha was unnecessary. Be such that TNS are in L B R and are definable, right? And now fix some A in R such that TNS are definable from B A okay, and you can take standard from maybe. Yeah, that's, I guess I want to do that. No, I can just say definable from B and A. Why can I say definable if not everything is definable from B and A being a real, right? There could be an ordinal parameter. But what do I want to do? I want to pick trees that project away, so I can take the least such trees, right? Definable from B and A, minimize the ordinal parameter. Or yes.
Is it
So
not,
basically,
is it not
yeah.
directly true from the coding, from coding lemma?
Well, yeah, I guess you could do it that way too. Yes, exactly. You could use coding lemma.
I mean, you already used coding lemma to get the B, right? So B already defines S and T very absolutely.
Well, for that you just need the easy coding lemma.
Yeah, okay. No, you don't need the full strength of the coding.
But you're right. So by coding lemma, but you don't even need coding lemma, I guess. So if you don't know coding lemma, what you could do is you could pick the B that where this TNS should appear, and then you use, and then you can minimize TNS. So you probably need.
Oh, okay. So you can find B just because of
You probably need
its
coding lemma
condensation,
anyway.
but maybe condensation gives you a B, something like it must appear at some. I don't know. Maybe no, that's nonsense. It's
I
not
think
here.
if you write the proof somewhere, coding lemma will appear somewhere. So, so let's say by coding lemma,
What kind of object is B?
B is a set of reals.
Okay.
My coding lemma, yes, is sigma 1 from B and some real, which is A. Okay. Okay, so why did I go to B instead of TNS? Well, because I wanted this to be elementary substructure. So now we can find sigma in power set of omega 1 of R such that L B intersection sigma R intersection sigma is sigma 1 elementary, or in fact fully elementary, in well, that's not the right way of writing. So there is an embedding. Let's just write there is an embedding such that there exists chain so that area of B intersection sigma is B, and area restricted to sigma is identity, which is trivial. I mean, geometry to sigma, that has to be identity. Okay, so you may ask, how did I find it? How can I find this? We don't exactly need this, but because these things are important, let me tell you why. Oh, by the way, that was. Okay, so why? So ADR implies for every A sharp exists, right? And now, so what we do is so to find sigma as above, find sigma such that L B sharp intersection sigma intersection R is sigma. And if you remember from last time, we proved that this is possible, right? You can always saturate, because it's a club filter, is an ultra filter on P omega 1 of R. This is in P omega 1 of R. Find sigma in P omega 1 of R. Okay, but now you really have, so we now have with this sigma, you have J from L, because this will be LB intersection sigma into L. You can also just take account of substructure. Again, I think I'm just making it more complicated. Okay. So you can find such a sigma. What do I mean by such a sigma? Sorry. Sigma like this. That there is an embedding from there to there. Okay, but now B, but this from the smaller model, you know, right? We now have.
Sorry, just for the sharps, did we prove this that the sharps exist? So what is the
No.
reason for this? Is this
No, I didn't prove, but that's not too hard because there
just
are,
because measurable cardinal path? Or?
yeah, right, there are measurable cardinals. But I'm not really sure if I can finish the proof with just the trees. Because if I now force over this countable thingy, of course, the new real will either be in the projection of big T or in the projection of big S, right? But what if it's not in the projection of the collapsed versions? So I think I should have used the sort of flipping function. I mean the homogeneity systems. Mm. I mean, the really hard proof is to use the homogeneity systems, but is it really necessary? Hmm. Hmm. Maybe we try some other way. How about we?
Just
Yeah.
just for my understanding, because I'm just slow here. What is the J? Yeah, how did you get you got it from this sigma? But what is?
Well,
Can you say what the
that's a
J?
good question.
Can you say what the J is?
I don't think this is the one. Can I just prove this is not the one that's gonna work? Let me. I think we just want to prove do it differently. Then I can tell you what J is because we might need it later on. Every set of reals. Let me erase this and well, that was the statement was correct, but the proof was not. I think we just want to put the tree and then stick it to just immediately prove the full version. Directly prove the full version. Yeah. So Okay. Yeah. So what you want to do is this. Right. So now notice that so for every sigma, notice that for every sigma in P omega 1 of R, such that R intersection L of T S sigma equals sigma, L T S sigma thinks T and S are sigma complementing. I.e., if P has size sigma, then it's forced by P that the projection of T is R dot minus projection of S. So the set of sigma that have this property is measure one, just like we did last time. And why is this true? Well, because T and S are trees on V, right? So why pick sigma such that LTS sigma intersection R is sigma. And now let G be any generic, any LTS sigma generic for a poset of size sigma, right? Then LTS sigma G is going to think that projection T is equal to R minus projection S. Because if I fix, right? Because if X is in R intersection L, yeah, S sigma G. So if I real here, and then X is in projection T in V, right? Then V thinks X is in projection T if and only if X is not in the projection of S. And so now use absoluteness. If X gets into, you want to see that right? This is absoluteness, right? Pick an X. You want to see it's either in the projection of T or in the projection of S. Well, in V, it's either in projection of T or in projection of S. But then by absoluteness, it would be the same would be true here. Right. Okay, so we now know for measure, and remember the set of sigma with this property is measure one. So we now know that for measure one many sigma, that statement is true, and then we just take a product. Right. So if we now take the product of L ds sigma by mu, where mu is the solving measure, this will be a model of the form pi mu t, pi mu s, and r, and L of pi mu t and pi mu s are the thing that pi mu t, pi mu s is R complementing. Okay, so it's a bit, I mean, the proof is, so how do we prove this theorem? The theorem we wanted to prove is that every set is R universally bare. Okay, so we first use this, so first use the fact that every set is Suslin, right? Now, suppose we have this poset P, and we want to prove that A is universally, has an R complementing right? That some set of reals A has are complementing. Okay. Maybe it's better if I just write it again because otherwise it was a mess anyway. Let's just write it again. Proof of the fix A want to see if P is of size R, then there is TS in V such that P forces section T is and section T is A. Right? So what we do is we fix TNS arbitrary high. So fix some B such that P is in LBR. Right? So P is, we can now go even further to find the trees. And now fix C such that the theta of LBR is less than the wage round of C, and LCR has trees yes on some kappa which is greater than that. I don't know if this makes sense. And projection T is A, and projection T is R minus projection S. Right, so you want to pick these trees high up. And now we need a version of this as well. Right. So now we apply. Now we do the above trick. Find for almost all sigma mu, almost all sigma, we have L B, a version of this B, right? B intersection, or C, I think I want, well, we can put it intersection sigma. Sigma think that TS are sigma complementing. And now you take the, so, but if you now take the product, L yes, P intersection sigma, C intersection sigma, sigma, this will end up being L of phi mu T by mu S B T R. And so, right, and P now, the poset P is in this model. So P now forces that these two are complementing. By mu T by mu S are okay. But, sorry, I have to go. I look forward to seeing the recording later.
Why is this reflected to V now? This fact, this forcing, like the trees are complementing. Is this absolute to be? I mean, I believe that it's true in this L of high.
I guess you want to, yeah, you want to make sure that all the, well, like all the names would have to be there as well. So you have to even fix another set of, there could be a name which is not, let's see, what's a name? A name is, you can do it name by name, right?
For each reel, for each
Yeah.
name for a reel, you can do it, and then okay, I see.
Yeah. Mm. Yeah. Yeah, you're right. I mean, maybe we should be a little bit careful. Let's see if you do. You don't want to do name by name, right? So what's going to be your final representation? Well, you want. Oh. I think you just want to take the join of all of these trees.
Yeah, that sounds right.
Right. But it's not well ordered, so. Like, for example, if you collapse the reals to be omega, then I mean, you will collapse a lot of things to be omega. So
I mean, the thing you wrote first is I believe now with the omega UB that you claim.
right, that's okay.
That's okay. Yeah.
But if you want RUB, then let's see. So here you would have some problems. It shows that each model thinks it is RUB. No, I think it's okay, right? Because let's see, is it okay or not? Because what if your poset comes higher? Yeah, you don't know if. Mm-hmm. Mm-hmm.
You somehow want to reflect all the names of reels to some bounded below theta point, right?
Yes.
For a given for fixed forcing.
Mm-hmm.
Is that possible? Can you?
Well, it's enough to prove probably for col omega r, and then I mean, and then the reals you cannot bound the reals where the names for reals show up, right? Because every ordinal less than theta will be of size r. But it's okay because this forcing.
Can you once again briefly say what's the issue?
I think there is no issue. It's just the way I wrote it. I think it. Let me try to write another time. Okay, so we want to prove. Here I want to see the ADR implies every set is our set of reals. Is R UB. So I think you want to say it's enough to show every set of reals is called omega, is UB for call omega R. Call omega R. Okay, so now we say, okay, fix A and let TS be complementing such that A equals projection T, right? And projection T is okay. So now what we say is let U be I mu. Well, what we want to say is claim. What we are claiming now is suppose that I mu T, I mu S are complementing that the forcing, sorry, let me just that the all omega R forces that I mu T, I mu S are complementing. Okay, so what is the proof? So for this, it's enough to prove that in each of the levels they are complementing, right? So because names for reals are bodied by sets of reals, enough to prove that for every B, L, I, mu T, I, mu S, and B things that is forced by call omega R, that the name coded by B, right? That pi mu T and pi mu S, that pi mu T and pi mu S are complementing. Okay, and so for this, we do the trick that we had. So for this, we have that for mu almost all sigma, L, T, S, D intersection sigma, sigma things that call omega sigma forces that projection T and projection S are complementing. For which it follows by ultra power construction that L I mu T thinks what we want.
And did you use that? Did you use the forcing? That the forcing was fixed to this call omega sigma? No, right? It was just any fixed forcing of size R.
Right, because that's just enough for this one.
Yeah.
But you could repeat the same for any forcing.
Yes. Okay.
But this is the universal forcing of size R. Yes. Okay, now it took a long time to prove this. The important thing is that, so corollary to this lemma is that suppose any is a set of reals, and we're assuming ADR, right? Assume ADR. Suppose A is set of reals, then and G is called omega, and G is called omega R generic, then in VG there is J from L AR into L the proof of this is that you just apply what we did to A sharp. So you look at because A sharp is right, so use the following.
Can you not just restrict the super compactness embedding at the pi mu?
But this is RG, right?
Ah, sorry. Yes.
Well, you have to look at there is J such that J of A is AG. Oh, okay, so the lemma says that ADR implies for every A set of reals, A sharp exists. And I think this is in the derived models theorem paper by Steele. Basically, you have measurable cardinals above any set. The proof is ADR implies, or AD just AD implies already, I think. Theta is the limit of measurable cardinals, but it doesn't mean A sharp exists. But what is true, so A is this fact, and B, which we did already, for every A that exists B, such that not only B is not in LAR, basically, this is what you want. Without this, having theta limit of measurables doesn't do it. You want a measurable cardinal above theta. So what this means, what B implies, so A gives a measurable cardinal above theta of LAR. This is what you want. You want the measurable to be above theta, not above. Yeah. You want this measurable to be really R measurable, so that there is no surjection from reals onto it. And then you can run the usual theory.
B is not a consequence of AD, right?
B is a constant, this is ADR, sorry. ADR implies B. Right. And then what you do to get the embedding is you take a representation for A sharp. I mean, you have to, it's again non-trivial, right? Because you would have to prove, for example, you have to prove, so why is, this is the proof of lemma. So why is it non-trivial? I'm missing something. It's because even if you take A sharp, right? Suppose you need to see that A sharp. You take A sharp, you interpret it, you get A G sharp, and right. But this is, if you just write down all the theory and see how the theory is working out, I think you'll get this. Right? Because you have you probably even already have it. Yeah, you probably already have it because we already know that at the countable level that's true, right? So why is this gonna be okay? Because we already know. So pick. Okay, want to see the above. I.e. that A sharp G is A G sharp, for example. Right, so pick PS for A and U W for A sharp, and pick sigma. So pick sigma such that R intersection L PS U W A intersection sigma A sharp intersection sigma equals sigma. Right? But now what does this model think? This model thinks that if you do the forcing, right? So let M be this L T S U W A intersection sigma A sharp intersection sigma sigma. So M thinks that it's forced by collapse omega sigma that A intersect that A intersection sigma let's call these guys names, right? So I'm going to call this A sigma and this A sigma sharp. So if I now force, I'll get that A sigma sharp G is equal to a sigma interpretation G sharp. Because of the way, because these were the real trees, right? And so from here it follows that if you now do the product, A intersection sigma, A sharp intersection sigma product mu, which is now L by mu T by mu S by mu U by mu W A sharp R, right? So it's M infinity, then M infinity thinks that it's forced by omega R that A sharp T is A G sharp. If you want to verify this, you have to just go see what it means to be A sharp. So imagine some theory is here, right? Then then because these were the real trees, you can see that that must be fine. Anyway, I mean, we can talk about it next time. Just try to see that this is true. If you are confused. Okay, so that's. I think this is all the background that we need. And now maybe I tell you a little bit what comes.
Is it somehow that the standard proof of this fact is a choice argument and the supercompactness measure lets us circumvent this? Because that you can commute these operations, the sharp and the extending to the forcing extension is true in ZFC, right? It's just
No, it's not. You usually need something like a Woodin or that's not
okay.
true. Even I mean in this Aspero Schindler paper they call it productive, right? So productive. This means that so A is UB. So it's not known. Just for any UB set, right? It's not known that A that exists X AG is there exists X AG. So projection of A, it's better to write as projection because X confuses, right? That projection of A as a set of reals, then you take G of that, its extension. Is it equal to, you first take AG and then you project. So I said it's not true, it's not known if it's true. I don't know if there's a counterexample, but if you want to get the equality, you usually need some Woodin or you need some extra thing. And so for example, I guess if A sharp itself was university pair, then this probably would be true.
I see. I think that's how I've seen the argument in Wooden's book.
Mm-hmm.
He says somehow if the sharp is UB or the sharp is home or something, and then
Yeah, you need something like that. Well, I think this is correct. If I didn't get it correctly, then we can. I don't want to get into proving it because it will be quite messy. Yeah. Yeah.
Sorry, is the not known part like not known and open, or not known and supposed to be trivially false if you think about it?
This, I think it's open if it's always true. I think it might have even appeared in the first paper on university pair sets.
Hmm.
You can check.
Hmm.
But if you have class of Woodens, then this is true.
Mm-hmm. Mm-hmm.
On the ADR, it's true. Right. So let me see where we are. Yeah. Or maybe we finish here and then I will. So what comes next is we are done with all of the what we now will prove is just there is an embedding that there is an ideal. So first step is to prove that there is a.
sorry, but about the embedding now, is it just that you map the indiscernibles to the indiscernibles, and that gives you an embedding?
You talk about the other one that I wrote?
I mean, you talked about this sharp because you wanted the sharp to get an embedding J.
Yeah. You send indiscernibles to indiscernibles. Yes, exactly.
That's it. Okay.
Mm-hmm. you can do it with, I mean, I don't want to get into inequality. These things are, once you know the inner model, like gamma wooding stuff, then this is much straightforward of this. Because you have A itself is in a derived model of some omega woodings. And then you did this a little forcing, then you can iterate, do another generous iteration, and put now AG into the other derived model. Right. Okay, so what is next? We don't have much time, so why don't I just tell you what we're gonna do? So we want to force H plus over a model of okay. So the forcing is gonna be we force with, so step one, we're going to force with our forcing will be collapse omega 1 r star collapse or add calling subset to omega 2. Right, so P forces choice. P forces ZFC plus CH. So why Z? Well, CH obviously the case. So fact one, that important fact is that P is countably closed. P is countably closed or countably closed, and DC holds, right? So P doesn't collapse omega 1. That's the first fact. The other thing that you want to note in towards proving that ZFC is true. So if I start working in V, right, so let GH be and omega 2 generic, and now we're working VG. So so VG thinks that theta is omega 2 plus DC omega 1. So why is theta omega 2? So theta is greater than, less than or equal to omega 2. Because if alpha is less than omega 2, less than theta, then we have some function that on 2, and f in D, right? So we already had that function, and G that maps omega 1 on 2. So RT alpha is less than omega 2, so equal to omega 1. Okay, but why is theta not collapsed? So y is theta a cardinal, right? That's the other thing we should discuss. Well, so suppose not. Suppose theta is not a cardinal. If it's not a cardinal and omega 1 is a cardinal, then theta is of size omega 1, right? Suppose cardinality of theta is omega 1, and let f be a function from omega 1 theta, f in Vg, right? So let me write like this.
And the forcing is just size R, right?
Yeah. So now you look at, so, but then you look at, right? So now for define h from all omega 1 r into theta onto by h, you can, well, these times r, right? You could take h condition and a real, and you could say, well, this is alpha if P forces that f dot g gamma x is equal to alpha, where gamma x is the real coordinate, is the ordinal coordinate by x, and then 0 otherwise, right? Then h will be onto. So h is on. Okay, so that's that. But then, so why? But it's important to prove that dc omega 1 is true, because without dc omega 1, you will not be able to prove that the next forcing, which is now omega 1 closed, right? That the next forcing preserves omega 1. You will not be able to prove that. So it's important, and then you will not be able to prove that omega 2 is preserved, right? So dc omega 1 is also true. So why is dc omega 1 true? Well, this is because dc omega 1, what does it say? If you have a tree which is countably closed, then there is a branch of length omega 1, right? But it's enough to assume that the tree is on sets of reals. So dc omega 1 says if R is omega closed tree, so any countable chain has upper bound, then it has omega 1 branch. There's an omega 1 branch. But we can assume, so dc omega 1 in Vg, right? This is dc omega 1 in Vg. So enough to show, so want to see that Vg thinks dc omega 1 is true, but it's in, so peak R in Vg, and but then we can translate R onto power set of reals, right? So can find R prime on power set of reals of V, and embedding J from R prime onto R prime again. It will be omega closed, I guess, anyway. So why can we do that? Well, because any set in V, before we did the forcing, any set was definable from a set of reals and some ordinal, right? So we can reduce the members of R. R could be on any set, but you can reduce it onto things that define members of R, which are these guys, right? And now theta is of size, so because theta is of size, theta is of So because theta is regular in V, we can find beta less than theta such that R prime restricted on the set of reals such that if their wage rank is less than beta is omega closed. But now you can perform what you want because, right? But now you can do because R prime is well ordered. But now R prime restricted to a subset of R. This is R of V.
Do you also need somehow that it doesn't have leaves still, the R prime?
Can you say again?
Do you need that it doesn't have any leaves, the R prime?
Well, it cannot, right? Because it embeds into and yes, you need to prove
the restriction, I mean.
Right, and it has the property, the DC property. So it's
yeah. So
but you can do that, right? You can, because you can, yeah. That's okay because theta is inaccessible. So anytime you have a leaf, you want to find the its upper bound, go to a place where you have it. If you keep closing under that operation, you'll never reach theta. So
yeah, I believe it.
Omega close, but the plus R prime and has no leaves. This leaf is V as but now this is well ordered, and so you can just pick any sequence you want. Okay, so that's that. And DC omega 1 is important because without DC omega 1, you wouldn't be able to prove that omega 2 is not collapsed, right? Okay, but once you add the coin subset to omega 2, then that's it. You will order everything, right? So now it follows that theta is a cardinal.
So when you write the R prime is on, it's on power set of R of V. Yeah, okay, I see.
So theta is a cardinal in VG, and so add 1 omega 2 forces here again. We use the fact that everything is definable from, right? We use this hypothesis that V is L of power set of reals. So everything is definable from sets of reals, and so it's just enough to well order. Yeah.
I'm slightly suspicious still, but maybe this is unnecessary. The R prime is not really in V, is it? It's in VG, or is it in V?
Yeah, it's in VG, but you can still do it, right? VG is G is a small forcing compared to theta. G is just of size R.
And so it's still regular afterwards. Is that true? Like.
Right, so theta is R inaccessible. There's no map from reals onto theta, which is cofinal.
I mean, it's omega 1 now, right? So of course.
Right, so there's no map from omega 1 onto omega 2, which is cofinal, which means you can keep closing under this operation of putting the upper bounds for leaves.
Okay.
Right?
Yes. So yeah, you're using regularity of omega 1 of VG, actually, right? I mean.
Right.
Which is. Yeah.
All right, so this is this. And then the next step is this is step 1. Step 1 just force choice. Now step 2 is where we get an ideal. So step 2 basically want to see that now NS. Let me just look at the notes. That the NS omega 1 R the non-stationary ideal on power set of omega 1 of R. So, and S on is precipitous ideal and a little bit more, and has the, well, let me write, but then I will not define it, and has the ordinal covering property. That's the ordinal covering property relative to V. This is want to see in VG star H. Okay, what does it mean, the ordinal covering property? Remember this theorems we were proving that you had some, we proved, for example, that the generic algebra power is the same as the algebra power by supercompactness measure, which came down to proving that if you have a function from on a measure one set that picks ordinals, then in V we can find another measure one set and another function which almost always agrees with the function you had before. So this ordinal covering property would guarantee the well-foundedness of the algebra. So it is what will guarantee precipitousness, basically. But the more important thing would be is that the generic algebra power given by this ideal will be obtained in the collapsing when you collapse the reals to be of size omega 1, which is what will ultimately guarantee the denseness. But it's this will be the first step, and for this we have to use the UP fact we proved today. So that fact comes into the proof of this. So this is going to be the next main thing. But we don't have any. We don't need any more background stuff. I think now we just proved the theorem.
I might be still confused about how to get the beta, I think, because the R prime has still height omega 1 of VG, right?
R prime, well, R prime is on power set of reals of V, which is of height omega 2. It's height theta.
No, but it's a, you want DC omega 1 means you have a tree of height omega 1, right? Which is countably closed and there's no leaves, and you want to find an omega 1 branch.
Right.
Is that what you're saying?
Yes, so you need to put all the, every time you see a leaf, you have to put an upper bound. Right, so imagine you're at some stage. Now there are lots of leaves. So look at the least place, which has all of the upper bounds for the leaves that you see. Right, that's below theta, because otherwise you would have a cofinal map from reals onto omega onto theta. Each time you have an initial segment of this R prime, all the leaves show up before you reach theta. Otherwise, you have a cofinal map onto theta. Is that making sense?
Because
So
the tree is somehow still
Well,
counted in VG.
the R prime does not have any leaves. The big R prime.
Yes.
So how to get beta? Suppose gamma is less than theta, and so delta gamma is instead of A, such that rate rank A is less than gamma, right? Now there is psi less than theta, such that all leaves of R prime restricted to delta gamma have upper bound in delta psi.
Oh, sorry, theta is collapsed to omega 2, right?
Yes.
Theta is omega 2, not omega 1. Okay, yeah, sorry.
Yes.
I was
NCH is true. It's not just that it's omega 1. NCH is true.
and CH is true because
So you don't have too many leaves here, right?
You didn't add any reals, of course, because the forcing was omega closed. Okay.
Forcing is omega closed, makes continuum omega 1,
Okay.
and
Okay.
theta is, yeah,
Theta is omega 2, and that's why you can do the process.
right.
It's
Yes,
an omega 1 process, but you cannot reach omega 2.
exactly. So I don't have to finish this way, and so on,
Yeah, it's just it's clear. It's clear.
and so on. Okay, so next time I want to start proving this fact, and then so I might need. I was a bit unprepared today, but next time, when is next time? Next time will be after the winter break.
I think it will be
And
8th by, like, or 9th by standard
Ninth.
calendar.